Engineering, National Institute of Technology, Durgapur, India. She received the BSc degree honors in physics and the BTech degree in computer science and technology from University of Calcutta and the ME degree in computer science and engineering and the PhD degree in engineering from Jadavpur University. Since 1994, she has been with the Department of Computer Science and Engineering, National Institute of Technology, Durgapur, and acted as the head of the department during 2007 to 2009 and 2019 to 2021. Her research interests include subcomputing, multi-objective evolutionary computing, fuzzy logic, fuzzy decision making, artificial neural network, machine learning, and pattern classification. She has 75 publications, including books, book chapter, conference, and journal papers. Under her supervision, 8 research scholars have been awarded PhD degree and 6 scholars are currently working. She is associated with 4 projects sponsored by DST and TCS. She is senior member of IEEE and acted as the chairperson of IEEE CIS Kolkata chapter for last 2 years from 2021 to 2022. Now I welcome Professor Tandra Pal ma'am to deliver his lecture to deliver her lecture. Now it's up to you, ma'am.
Thank you for your nice introduction. Good morning. At first, I sincerely thank the organization for inviting me to share my knowledge in this event. Let us first upload my slide. Is it visible? Hello?
No, ma'am, till now
No,
it's not
ma'am.
visible.
It's visible. Visible. It is visible.
Okay. Full screen, okay? Now, to the organizer, please actually one by one, the participants are trying to enter the event. So how can we, and it is coming in the screen. Okay, I have handled already it, okay? My talk is on the classification of waste material. Now, here I would like to inform you that my talk is not very compact, and I will not emphasize on the derivation or mathematics. I will just introduce with few topics, for example, multilayer perceptron, CNN. Professor Panda, Ganapati Panda has already given a nice lecture on CNN, so I will try to make it brief. Now, and also little bit result on waste classification. Now, we already are very much aware about the waste management. Due to urbanization, different organization, including the industry, there are so many waste materials, and we have to process it properly. For example, in my home, in each and every day, a bag full of waste materials, I throw it in the basket. Even in our institute, there are so many computers which are obsolete. And even for the management of those obsolete things and other materials, waste materials, we need to call the tender so that they can take it to make our institute clean and healthy. Now you will see nowadays there are not only one dustbin together, more than one. Maybe one basket for the dry material, one basket for the wet material, one basket for the biodegradable material, another basket is non-biodegradable material. This is nothing but classification manually. Manually, we are trying to classify the materials. The question is why? This waste material actually, we want to utilize it, maybe through recycle bin. So it is very important to classify them. But manual classification, of course, is not reliable and there may be a mixture. That's why the pattern classification is important. That is, classify the waste materials into different categories so that they can be processed in future or maybe recycled for future purpose so that we can use it. Now we know what is waste. We need to discard it or which will be discarded in near future. And also different types. For example, it may be solid, it may be liquid, or maybe semi-solid. And they are being generated from my home, domestic, industry, and some commercial, especially the power plant, different types of plant, and even for agricultural mining operations. So these are the sources of producing the waste materials. Now, my talk is on pattern classification for classifying biomedical waste. And I will use here, show and discuss little bit about multi-layer perceptron and CNN. Both are under the category of artificial neural network. And already from the previous lecture, you know that multi-layer perceptron is conventional neural network. Conventional, it uses conventional learning, and convolutional neural network is one type of deep learning technique. And another assumption here is that the input which will be provided to the neural network, whether MLP or CNN, they are in the form of numerical values or images. And the choice of the type of neural network depends on the format of the biomedical waste data. For example, for numerical values, mostly we choose multi-layer perceptron, and for CNN, we choose the image. And we have little bit discussion that numerical values can also be fed to CNN. So classification of hazardous and non-hazardous biomedical waste from numerical parametric values called features of the bio-waste, that is amount of mineral and their compositions in the bio-waste. That is, those characteristics, features means the characteristics which will help to identify the type of the waste. For example, for me, what are the features? My name, my age, my height, all these things. I think you know already what are the features. That is the information of the object, we have to provide it through some features. Okay. Any feed-forward neural network like multi-layer perceptron can be used as classifier. But sometimes numerical values are not available. Even if it is available, it takes time to extract the features, right, from those objects. So in that case, we use images of those objects. Now it's about multi-layer perceptron. In a neural network, it has been inspired from our nervous system, including the brain. Our brain contains about 10 to the power 11 billion nerve cells, which we call neurons. And each neuron is connected to other neurons through 10 to the power 4 connections. And sometimes actually the connections means they are connected to each other by synapses, a solid, not solid, semi-liquid material by which the signal passes from one neuron to other neuron. Now, the properties of the brain which we want to simulate in neural network, what are those? First of all, it can learn and recognize itself from experience. We are learning from our childhood, and based on our experiments, later we can recognize or identify the things. I have seen so many types of tables, but if a new type of table comes in the market, then I can also identify that it is table, right? So this is called learning from the experience. And it adapts to the environment. Actually, we are learning and we are exploiting our knowledge, previous experiments, experience, as well as we are exploring, that is, we are adding new knowledge. Okay. And this is actually done in neural network by adaptation of weight. Each connection between the neurons, between two neurons, is actually represented by weight. That is how strong and age it is represented by the values of the weight. It is robust. It is very important for real life application or problem. It should be robust. Robust means in an ideal situation, when we develop a model, it gives the correct result, proper result, optimal result, right? But when we do the experiment, then some of the assumptions about the parameters or environment that are not always available. For example, temperature, right? That may change. Some other parameter values which I have measured during my experiment, next time it may be changed, right? Or there may be even measurement error. So if actually these are called uncertainty, and it is the nature of life. So to tackle these changes or uncertainty, right, we have to make the system robust. What does it mean? If there is a change in the parameter values, then also it will work. It will give the result, and the result may not be optimal, but very close to optimal. Graceful degradation means there is a degradation in the performance. That is the quality of the result. However, it is acceptable. Okay. Now about artificial neural network. Here learning is based on modeling the adaptation in biological neural system. Okay. Humans have an ability to identify patterns within the accessible information with a high degree of accuracy. And in this case, we are trying to simulate it. Of course, it is not possible, I believe. And whenever we see a car or a bicycle, we can immediately recognize what they are. This is because we have learned over a period of time how a car or a bicycle looks like and what their distinguishing features are. This is very important, distinguishing features. Now, one participant has asked about the how many data, what should be the volume of the data. It depends. If there are so many features are not collected properly, right? There may be some redundant features. There may be some features which are not very relevant, or there may be some conflicting features. Okay. Then, of course, the training will not be proper. And also the samples, for example, when a child is learning, a supervisor is there, the mother, and she is telling it is apple, it is banana. So if the training is wrong, that is the information or decision, that is, if a guava of green color is told to the child that it is apple, then of course the learning will not be proper. So the data or training data which are being fed to the neural network, that is very important. There may be some noises. Noises means this output or the answer of the mother supervisor may not be correct because they are being produced by some operations or process, and there may be some noise. So if noise is filtered properly, then of course there will be some misclassification or will be more. Now it is also very costly to remove the noise. So it depends on where the data is reliable and sufficient. For example, if I show only the apple and banana, then of course it will not learn the other fruits. Okay, so it depends on many things, and also whether the data is balanced or not. That is, if among 100 samples, only 2 samples, that is the training data, is for apple and 99 is for banana. So there should be the balanced of different patterns or classes. Okay, so the features, whether it is important or not, what is the volume of the data, and more the complex the distribution, okay, or the problem, of course we need more samples, that is more examples. Okay. Now, artificial neural networks are computation systems that intend to imitate human learning capabilities via a complex architecture. Now, learning involves modifying the weights between the neurons. What is learning? Nothing, just the weight associated with the connection between the neurons, okay, that are being updated. So initially, we set it just randomly with any weight, and weight actually theoretically, the weight can vary from -infinity to +infinity. However, for proper training, we normalize it, maybe say -0.5 to +0.5, or maybe from 0 to 1, like that. Now, perceptron, a single neuron, actually, we call it perceptron, and this is the initial algorithm for learning. It has been used and developed in 1950s. However, a complex algorithm, multi-layer perceptron or multi-layer neural network, has been developed in 1980s. Now, this is about a single layer perceptron or only a node. Sometimes we call it a neuron, or we sometimes call it node, sometimes call it a perceptron, right? So a perceptron is simple binary classification algorithm, the simpler single layer, right? And helps to divide a set of input signal into 2 parts, either yes or no. That is binary output. That is the simplest version of the learning algorithm.
Ma'am, you got it muted.
Madam, you have been muted.
Madam, you muted, madam. Ma'am, kindly unmute yourself.
Okay, okay. Now I am audible, right?
Yes, ma'am. Yes, ma'am.
When I have been muted for a long time.
No, madam. On just now
Okay,
you have
maybe
muted.
by chance,
Yes.
by mistake, I have done
Yes,
it.
yes, yes.
Okay. So unlike many other classification algorithm, the perceptron is modeled based on the neuron of our nervous system and has an ability to learn and solve complex problem. But in this case, by single layer, we are considering the simplest model. What is that? A set of inputs are coming. What are the inputs? X1, X2. That is, here we have assumed 5. It will differ, right? Based on the problem. Now each, that is, this is here, the X1 will come, X2 will come. From where? From another neuron actually comes. But here we are considering only one neuron. Now it is connected to the neuron via a connection. Now, actually, the connection means it is I have mentioned that weight is associated with each and every connection. Say the weight is W1. Okay. So what is the effective output input to the neuron for this? This is X1 W1. Similarly, for this, it is X2 W2, and for X5, the effective input to the neuron is X5 into W5. Now, what is the net input? That is the total input, summation of this weighted input. That is X1. Most probably it is there. Yeah. So it is W1 X1 plus W2 X2 and Wn Xn for n inputs. Okay. And there is a bias. I will tell you later what is bias. Here we assume that is an extra connection input is there, which we assume as 1, and the corresponding weight is W0. Okay. So that net input to the perceptron is this W0 plus Wi summation of Wi xi. So when it is 1, then the output will be 1. Otherwise, it will be -1 or 0. That is, it may be 1 or 0 or maybe 1 or -1. Okay. So in this case, we are assuming only 2 classes are there. One class is represented by 1 and another class is represented by -1 or 0. Okay. Now, I request during my discussion, if you have any doubt, you can interrupt me. Otherwise, the next talk will not be understood properly, I think. Okay. Now, in this case, you see there is a step function. It is, we have planned, or in single layer perceptron, a simple function is there. Why? Because based on the step function, that is, this will be actually, this function will be operated on this output. That is the output of the neuron, and that will be the final output of the perceptron. Okay. As in this case, only the output is either 0, 1. That's why we have used step function. But for complex problem, okay, it is not possible for the step function to give different outputs, different types of output. Even there may be the real values in the output. Now, so step function or the function associated with the perceptron, we call it activation function. Now, there may be different types of function, and generally for complex problem, we use sigmoid function or sigmoid function. Why? Because you see, for this type of problem, right, just we consider a straight line is actually the classifier. If it is on the left side, then it is one class. If it is in the right side, then in another class. But let us consider, say these are the samples or objects. Okay, then a single straight line has not cannot differentiate these two classes. One class actually is represented by the objects of most probably it is yellow color, and the other class is represented by the objects of red color. So there is no single class linear equation or straight line. In this case, two-dimensional, it is straight line. In 3 dimension, it will be a plane, right? And for more, it will be, we call it hyperplane. So it is not possible to classify these two classes. So it's a very complex problem. So in that case, we need non-linear sigmoid, for example, sigmoid or other function. Now, what is multi-layer perceptron? Okay. Actually, I have told you that I will just give the idea, right, for pattern classification using MLP and CNN, and some concept associated with it. And I think the research scholars and the young faculties, they may get the idea from it, and if necessary in future, if they need it for their teaching or research, then they will read it in detail. Okay, that is my purpose. Now, in a multi-layer perceptron, there are different layers. That's why it is called multi-layer. Now, how many layers? At least one input layer. Can you see my pointer cursor? This, I am moving in the input layer.
Yes, madam.
Yes. So this is the input layer, the first layer, and the final layer is the output layer. And the layer in between the input and output layer, it is called hidden layer. Now, why it is called multi-layer? Only 3 layers are there. Now, the hidden layers can be more than one. Okay. So we can summarize: one input layer, one output layer, and at least one hidden layer. Okay. Now, in multi-layer perceptron, the nodes of one layer is connected, all nodes of one layer is connected to the next layer, to all nodes. And similarly, all nodes of the hidden layer will be connected to all nodes of the output layer. In this case, the figure, the architecture of the multi-layer perceptron, we have drawn one node. That is, in this case, we have assumed there are 2 classes. If the output is 0, then one class. If the output is 1, then another class. But if more classes are there, then the output node will be, number of node will be more. Now, why 2 nodes are there in the input layer? Here I have assumed 2 features are there in the input. Okay. But if say number of features is say m, then there will be m such nodes. Not now. How many hidden layers are there? There is no such guideline. More the complex is the problem, more is the number of hidden layers. And how many hidden layers? That is also, there is no such guideline. Okay. We can take 1, we can take 2, we can take 3. But keep it in your mind, vanishing gradient, the term vanishing gradient problem is there. That is, if we take much more hidden layers, ultimately it will not be effective. Okay. I will try to tell you what is vanishing gradient, because error is minimized based on the gradient. Okay. It propagate from the output layer to the input layer. Let us leave it, otherwise it will be more confusing. Okay, so we can't take so many hidden layers. Okay, it will not be effective. So, and there is a theorem that only one hidden layer is sufficient to solve any problem of any level of complexity. Okay, however, you may need more number of nodes. Okay, and in our lab, we have used only one hidden layer. Okay, in the multi-layer perceptron. So it is convenient to take one hidden layer, and it is sufficient to solve any problem, even of high complexity. Okay, and there is no connection among the nodes of any layer. That is, there is no connection among the nodes of input layer, no connection among the nodes of hidden layer, and so on. So this is the architecture, okay, or structure of multi-layer perceptron. Now the back propagation. Now let us see what we do. We feed the input here, okay. This input, actually, what is the function of the input layer? Now, actually, my talk is up to 1 p.m. Hello, organizer. Hello.
Yes, ma'am.
Now, though I have started late,
Yes.
I am not claiming more time. So,
Okay, ma'am. You can
before,
continue whatever you have. You can continue. No problem from our end.
Okay. Okay. Thank you. But I will not go too much detail. Okay.
Okay, ma'am. Sure.
No problem. So in this case, in case of multi-layer perceptron, actually there is no processing here. Okay. Just it acts like a buffer. That is, if X is the input here, the output is also X. Okay. So there is no nothing complex activation function, just Y is equal to X. Okay. In this case, the activation function. And we already know that the output will be connected to all the inputs of the next layer. Here, and also this input, we know the model of the perceptron, the weight is associated with all the connections here. So the weighted input from this node as well as from this node, okay, will be summed up and will be activated by the activation function, and it will produce the output that will be connected to the output layer. And this is very simple. That is, we know the function of each and every neuron. So given the input, these outputs will be connected to the inputs of all hidden nodes, and the output of all hidden nodes will be provided to the output nodes, and finally the output will be produced. Okay, so given the input, output will be produced by this, it is called feed forward. So this is a pass, feed forward pass. Now how it will learn, this is very important. This is called error back propagation. That is, the output it generates, okay, will be compared to the given output. Multi-layer perceptron is supervised neural network. That is, output supervised means there is no physical presence of teacher. The output is known. If we consider input as the question, then the output is the answer. So for the data, each and every sample or pattern, okay, or object, the features are the input, and the corresponding class, if that is, if it is a classification problem, is the output. It is given. So the given output will be compared with the output computed by this neural network. Now it is being trained. So the answer or the output of the neural network may not be the same as the ideal answer, that is the given output. So error will be computed, the difference between them. Now, what is the next function? Actually, the weight will be updated based on the error. And the principle is you minimize the error. Okay. So there the error will be used for updating this weight, so that the principle is just a simple derivative, partial derivative, right? Del E by del W. We compute del E, where E is the error, and del W, where W is the weight. Okay. And based on this weight, we update this weight. Okay. So one iteration is done. Then another sample or pattern or object or training data is given, and again output is produced, and again we compute the error, and the error is back propagated to update the weight. Just we continue it. Very simple, right? Now this is called error back propagation. That is, error is being back propagated from the output layer to the input layer for updating the weight. And keep it in your mind that the weights between the hidden and output layers will be first updated, and then these will be updated. I'm not going into the detail of it. Okay. That's why it is called error back propagation. Okay. It is not feedback. Okay. Feedback means from output, it will come directly to the input. It is not that case. From my teaching experience, I have seen that the people cannot remember the difference between feedback and the error back propagation. Okay. So any question up to this? No. So you see, learning means the weights are being updated. How long? When you will see the weight updation is not being done. That is already trained based on the training data. That is how much knowledge it can gain. It has been gained. No more knowledge is there to get from the training data. Okay. So then error will not be reduced more. You think it is not that error will be zero, because I have mentioned already, there may be some noise. Error may not be zero. Okay. However, you will see while updating the weights with time or iteration, the error again will not be reduced. Then you will learn it has been conversed. That is, training is over, then you will stop it. Okay, now it is ready to identify any other pattern for which the output or class is not even given. Okay. Now I'm not going to that. Already I have told you what is the activation, what is the significance of activation function. But the bias, actually, the bias means, actually I have told W0 is the bias term. That is, there is a node, an extra node in the input layer as well as in the hidden layer, and weight is associated with it, but no actual input is there. We consider input as 1. Actually, this is for the constant term. For any equation, you will see at last there is a constant term. For example, straight line y is equal to mx plus c. This c is actually the bias, and m is the gradient, the orientation of the straight line. So that bias node is used for that purpose. It's already, I have given. Now about the hyperparameters. Now hyperparameters, we have told, actually the weight, this is called the design parameter. Or so this is being actually learned through the learning algorithm. But there are some other parameters which we call hyperparameter. For example, how many hidden layer, how many nodes, and also what will be the for example, here, in while we are adjusting the weight, say W equal to actually del W equal to del E by del W. Sorry, I could come with some board. Just a minute, let me check. Yeah. Just a minute. When we update the weight, okay, then there is a term called learning rate. How fast it will learn. Now, for that purpose, now in that case, it's sure that always we will try to make the learning fast. So always we will try to give the learning rate high. But there is some problem. That is, I have told that when weight there will not be changed or very little bit change in the weight, then we confirm that it has been converged, but not always. Okay. We may get stuck in local minima. What is that? For example, there are so many holes. Now, my aim is to go to the large hole. But in the path, there may be some small hole. So if I am not careful, I may I can fall in the small hole. Then actually that is going to the hole. This is based on the gradient descent, okay, of the error function. So if I fall on the small hole, there is no chance of get up from it and going to the large hole, which is my objective. Because the principle is you go down always, okay? There is no chance to go up or climb up. Now, if my step is very less and I become careful, then of course I will not fall down in the smaller holes. Finally, I will reach to the larger hole, my destination. Here, hole I am considering as the error. As we don't know the distribution of the input, so there may be multiple peaks, or that is multiple holes. But my objective is to go to the largest hole, that is the which corresponds to global optima. But my steps is more, right? Then it is very difficult to avoid the large hole. So I will fall down. So in this case, it is very important to decide the value of the learning constant. Okay. Now, if my steps, that is the learning constant, learning rate is high, then there may be, I can get stuck in the local minima. And if my step is very, very small, it will take much time to learn, right? So this is a problem in neural network to decide the value of the learning constant. And generally it varies from 0.1 to 0.001 like that. But this, we should be very much careful for that. Sometimes you have given, say, even 0.001, then also it may get stuck. So then you may need to change it accordingly. And there are some methods for which we can try to find the optimal value of the learning constant. But that is also time consuming. Okay. So this is called the tuning of the parameter value for the hyperparameter. But again, it is to be noted that in learning of the neural network, we don't update it It is fixed. Before we start learning, we have to decide, okay, about the hyperparameter values. So this is also important for machine learning. There are two types of parameters. One is hyperparameter and another is design parameter, which we are trying to design. And that is, in this case, weight is the design parameter, and hidden number of hidden layers, nodes in the hidden layer, and training size or batch size, all these things, the learning rate, these are the hyperparameters that you have to decide at first. Now, there's a concept for dropout. This is actually basically for generalization, rather we call it robustness. Dropout means what percentage of neurons should be randomly killed during each epoch to prevent overfitting. That is very important. What is overfitting? Overfitting problem is very common in any machine learning algorithm. Okay, what is that overfitting? Let us see. It's most probably, actually I have got very less time to prepare my slide, so I could not organize it properly. Yeah. Overfitting means, say, when we train the neural network, then we see, yes, error has been reduced and classification is also good for the training data. But if a test data is given, I think you know about the training and testing, and Professor Panda has also mentioned it. Say 100, the data size, available data size is 100, then actually we don't use all for the training. Because when I teach my child about, say, vegetables or the fruits, okay, which I am showing, that should not be tested whether my child can recognize it or not, because it can memorize it, okay, without learning the features in detail of the fruits, he can memorize it. And especially if I show the same apple every time, and that causes the overfitting. So overfitting means during training, if we use the training data for classification purpose, the classification accuracy will be good. But for test data, that is for a different data, right? The classification accuracy will be very poor. Why it happens? I have just mentioned it, that learning has not been proper, or the same samples we have shown differently, that is the diversities in the distribution of the data that has not been reflected in the training data. Again, the questions I have seen in the previous lecture, how many training data will be given? There is no answer. It depends about the quality of the data. If the quality is nice, even 50 samples can be enough for training. But if it is 500 samples or 5 lakhs, then also it may not be sufficient. It depends that whether we are training from all over the input space. That is, the samples from all over the space has been considered or not. If I take only a part of the input space as training and collect the training samples, then of course it will not learn. So overfitting means it gives good classification result for training data, but not for the test data. Okay. Now, in this case, you see, say here, we want to, this is the ideal function. This is not a classification, just I am considering the function approximation or regression, right? Actually, the same multilayer perceptron can be used for classification as well as for regression. Only the output you have to consider in a different way conceptually, but the computation is the same. So in this case, actually the samples are given, right? These samples are given. Just we have to find the function, approximate the function. Now this is actually the ideal. This is actually the ideal function we need to learn. However, the samples are given like this, because I have told you that samples, there are noises, and accurate samples, it is very difficult to get, not available always, because they are being produced by some processing or operations, okay, or by some experiment. It is not y is equal to x1 square plus x2 like that, okay. Now, in the first case, you see, say this is the classifier. That is very simple neural network model I have used. And it has given only the straight line. And if it is in this side, the sample, then just, sorry, it is not classification. So this is the function approximation. So of course, in this case, it's not trained properly. It has not been learned properly. It has not learned properly. It is called underfitting, that it has not understood anything about the function. But you see how nice it is. Okay. This is the function which have been produced. And these are the training data. So for all the training data, you see, just correct output it is giving. So with respect to training, it is very nice. But actually, this is a function, right? And you see, it does not represent the function. And if you take, for example, this a data here, then actual ideal output should be this, but it will give this output. Have you got it? This case is called the overfitting, and this case is called the underfitting. Okay, underfitting means it has not learned anything about the function, but here it has learned in such a way for the training input it gives the good results, very good results, but for test it giving very poor results. This is called the overfitting problem. Okay. Now about the bias and variance. Actually, for underfitting, there are two terms. Again, for the beginners, there are two terms, bias and variance. For underfitting problem, the bias is high, okay? And for overfitting problem, the variance is very high, okay? So this is very important to make a balance between bias and variance, okay? And in this case, you see, if you see how they are related with each other. So with time, bias is being decreased and variance is being increased. So if you train the network more and more, right, then you see the variance will be high and bias will be less. Okay. So the left side represent the underfitting and right side represent the overfitting. Okay. So what to do? We should avoid both underfitting and overfitting. And we have to stop the training in this point. But you see, here I can see the curve, but actually when learning will be going, then I don't know. Okay. What is that point? So that's the problem. how much I will train. It is not that you give more time for training, it will give better, it will be better trained. Just I am giving a simple example. Say I am here. Okay. For a simple subject, if I take more number of classes, then finally the student will not take care to understand the logic, internal logic. Just as I am repeating the same discussion, so just they will try to remember it. And in the and if the question is little bit different, which I have discussed, right? That is the answer. For answering it, they need to know the internal logic. Then they will fail. So this is also the problem. This is called also the overfitting. That is for simple data, rather simple, when the complexity is less, then we should not train the network for high time, for much time. But if the problem is very complex, then of course the training time will be more. That is actually the question. And underfitting means if I take very little bit classes, and even if I there is some knowledge or that is I am not giving the proper discussion, there are some many things wrong information, then it is called underfitting. Okay. So to avoid this problem, not underfitting, not overfitting, we have to be very careful about the bias and variance. Bias and variance, there are some mathematical representation, expression, and more theoretical things are there. You have to read it if you need. Just a minute. Let me see the previous slides which we have. Yeah, generalization. So that's why the generalization. So we apply generalization, some generalization method to avoid this overfitting or underfitting problem. So a model or network that is not sufficiently trained can fail to learn the hidden patterns in a complicated data set. Please, you see, hidden pattern means actually learning the input distribution. Learning a neural network means given a set of input data, it needs to find the pattern of distribution, how it is distributed in the input space. Okay. So the training should be in such a way that the distribution of pattern should be learned by the network properly. So if it is not sufficient, that is for the complex problem, if I take little less class, then there will be the underfitting problem. And I have told that bias is high for underfitting problem, and for overfitting, variance is very high. And in this case, a model that is too complex may fit the noise, not just the pattern, leading to overfitting. That is, if there is noise, as I am providing the training more and more, that noise also will be discussed many more times, right? Will be applied many more times. So I had to stop it, the overtraining. Okay, this is what to avoid the overfitting. Now, it is not that just you stop it, to avoid the overfitting. There are some other methods also, because we don't know when to stop it, some other methods to apply for generalization. Now let us see what is generalization. Again, say this is the ideal function, and these are these are the ideal function which are blinking, and these are the training data. Red small circle, it represents the training data. Okay. Now, based on the training data, this is the function we have learned. Okay. Now, in this case, you see it is a good approximation of the ideal data. This is the ideal data, ideal function, and this function has been approximated, that is the trained by the model. Now, let us see whether it is good or not. Say, this is the test data. Okay. Now, in this case, you see what is the error? This is the error, and it is acceptable, right? It is acceptable. So in this case, this model is generalized. Okay. Now, I'm not going more into it because time is not sufficient. Now, actually, in my lab, we have done a few works to make the multilayer perceptron generalized and robust. Okay, I am not going to that, and there are some methods for make it robust and generalization, right? That also I am not going. Just here I would like to tell you, actually, forget about the robustness. Say this is the error curve, right? So in this case, I have told you it tries to minimize the error. So in this case, the error will be minimized along the gradient of the error surface, and ultimately it will come here where the error is less. Now, this is to show the robustness. That is, if there is any change of parameter values, okay, of the model, then also it will not affect a lot. It will not hamper. Of course, the solution will be a little bit different from the optimal solution, but acceptable. Okay. Now, say this is the error curve. Now, it represents a specific state of the neural network. Here, Wij means actually a set of weights. I have told you so many weights are connected, associated with so many edges. So there are edges, connections between input and hidden layer, and also the edges between hidden and output layer. So a set of weights are associated between input and hidden layer, and another set of weights are associated between hidden and output layer. And so we can represent it by a weight matrix. Okay, so just you consider one iteration. After one iteration, a set of weights, and after the next iteration in the training, another set of weights. So in this case, the x-axis actually represents different iterations, and at that iteration, what is the corresponding weight? That is the overall weight of the network. And for that weight, there is an error corresponding to the problem. So in this case, just we have assumed this is the error curve. Okay, and when of course the error is very less, okay, least, then it will give us the global solution. Okay, so in this case, we are considering, actually it is not possible always to go to the global solution. Here I am considering that if error is up to this, then it is acceptable. Okay, and if we can go to this, of course it is the best situation. Now, in this case, you see, say somehow we have arrived here, that is the error is least and the solution is optimal. Now I have told you that parameters may vary. You may not control it, right? Always. And which you have measured, that is not the actual. There may be some error. There is the nature is full of uncertainty. for different parameters in our environment. So maybe due to this, okay, even the weight, which, for example, I have developed a chip based on the values after learning. But maybe during the design of that chip and making the chip, you cannot ensure that the value is which you have computed may differ. Okay, even a node can be damaged or a connection can be damaged. Okay, so that is the importance of making a system very robust. That is, if a node or a set of nodes is damaged, then also it will work. Of course, the performance will be less, but acceptable. But keep it in your mind that, of course, there is a threshold. That is how many nodes can be damaged, right? Among 100 nodes, if 15 nodes are damaged, of course, that network will not work. But maybe if 5% of the nodes are damaged or 5% of the edges are damaged, that is why it becomes zero, right? No connection. But assuming that connection is there, then it should work. Okay, now this is the how to do it. So if there is any parameter value, then of course, in this case, you see the error will be increased from this point to this point, only this little bit change you see. Sorry. Okay. So this is not a robust system, right? So what to do it? Keep it in your mind one term, smoothness. Smoothness is very important to be very stable or robust, right? That is, you can withstand the hot as well as cold. May not be very cold, may not be very hot. You should not be very sensitive to any parameter value. Okay, that's actually the smoothness or stability, right? So in this case, instead of going to this global or best result, let us, if we consider this one, right? This is the robust solution. It is not optimal here. Okay, how? Because even if the change of parameter values changes the weights, right? This amount compared is very high. The range rather than the range here. Okay, so instead of considering or getting this optimal solution, we want to get rather more interested on getting the robust solution. Okay, this is the importance of robustness. And you see, this is more smooth than this. Okay, you see here the gradient is high, slope is very high, but here the slope is very less. Okay, value of the slope. Now, there are so many regularization methods, and my scholars have done so many things on MLP. I am not going to that. And L2 norm is one of the tools for making the system. I am trying now to finish it, right? Now, thus I have collected, right? The one thing I should mention here, the slides are prepared by my scholars, and some slides we have collected from some documents. Okay, many slides, of course, we have made, but some information we have copied it from other documents. Now, in this case, just I am showing the result of multi-layer perceptron, which we have discussed a lot. In this case, we have considered 1, 2, 3, 4, 5 types of classes are there. That is the waste material, maybe of food type, maybe of plastic type, maybe of metal type or paper type, or The remaining, I am telling it is general type, right? And in this case, most probably you are as the classification confusion matrix, right? And negative false, positive false, negative true, all these things I'm not going to it. If you are interested in machine learning, you should know what is that. And based on that values, actually, we create the values, we compute the values of precision, recall, F1 score, support, all these things, and more the values, better it is. Okay. So in this case, using those, actually they have used the images, right? Using the images, they have, but they have extracted the features from the image and then they have fed it to the multi-layer perceptron. Okay, not the CNN, convolutional neural network, and they have got good enough results. Okay, I'm not going into that, just to convince you. Yes, the people are doing the classification of biomedical image West. Now it is about the CNN. Professor Panda sir has talked a lot of it, so I am not going into it. Just this is the earlier model used for bio-OST classification. This is called LINET. Okay, and just one thing again. There was a question, what is the difference between DNN and CNN? Professor Panda sir has given the answer. I am again repeating it. For multi-layer perceptron, I have told you we need to provide the features in the input layer, right? So in this case, actually the features are numerical values. But of course, this feature extraction is very important, and you need to extract the features. That's feature extraction method, first of all. Next is you have to find the significant features. This is called feature selection, right? Significant features and irrelevant or insignificant features, if you can avoid, then of course it will learn in a better way and in very less time. So in that case, of course, the conventional machine learning network algorithm or neural network, including the multi-layer perceptron, will give good result. But it is not, it is of course also costly, but it is not always possible to find the features, right? In that case, not the features, the whole object or whole the sample itself, I will present it to the neural network, and that is actually the image. That is the image of a bird or image of a fruit instead of features of the fruit. What are the features of the fruit? Maybe its shape, maybe its color, maybe the smoothness of the surface, and also you see that why color is important. It is green for guava, and for apple also there may be green. But you see the texture of the surface for guava, it is coarse, right? Not so smooth, but for apple it is smooth. So in this case, you can see the texture of the surface as well as the color and as well as the size, right? For tomato, it is generally less than the apple. So these are the features, significant features, which we need to present to the neural network. So we need to be expert. It is not always the vegetables and fruits. There are so many types of inputs. So it depends on the expertise. So what features we will consider, or some other experiment to find the what features are how much significant. That is also there. You will see. And based on that, that is called feature selection method. Given a set of features, which feature we will select. Okay. But if I don't want to bother about it, then I will use CNN. That is just the image of the sample will be provided. What is image? Actually, it may be the pixel values. Okay. Now, what is the problem for it? The problem is if the features are given, that is, if I take the classes, right, and give importance on the significant topics and less importance in the non-significant topics, then accordingly the student will learn it. But if I tell them, you just collect the books and you go through it, right? Then of course they need to search different books and to read different books and read, and then to understand which books is more important and go through that book. And also after so many times studying, they will understand this is the significant thing for this subject and this I can avoid. Okay. So that's why the CNN, there is no such features. Okay. So the CNN will find the features and CNN will find the significant features and will try to avoid the insignificant features. So you see what is the responsibility of CNN and or any deep learning method. This is called feature engineering. Feature engineering part is done by the CNN, which is not done by the conventional machine learning or multi-layer perceptron. Have you got it? So obviously, you have to give many data. That is, volume of the data will be very high. Okay. And to extract the features, it's a long process. And you see in this case, all the layers that has already described, it's really unfortunate that I don't need to explain it. Convolution layer, pooling layer, padding layer, ReLU, all these things is required only for feature engineering. So the dense part, these you can consider only as the MLP, and the features are presented here and we have already discussed it. And all these things are only the extracting the features from the given input, and it is just an image. Have you got it? So already you know CNN. And again, I'm repeating the difference. Those has mentioned it. Just as it is very important, and many students even cannot understand the difference, basic difference. That is, feature engineering part is not there in multi-layer perceptron. The answer is so many hidden layers are there. That's why it is called. If many layers are there, then it is deep learning, right? But many layers are there only for feature engineering. Okay. And you know already about the convolution operation, kernel, filters, strides. Okay. All these things, I am not going through it. I am not going through it. Just I am showing this is the different steps. And the same that is given here, the medical cap, the image of the cap, of course, and different layers are doing it. Ultimately, you see, it is giving yes, it is medical cap. So if there are, for example, 5 patterns, so there will be 5 such output. One for medical cap, another for gloves, all these things. Okay, this is being done by the and this is one simulation results from other experiment. And these different classes: gloves, gauges, medical cap, medical glass, shoe cover, test tube, urine bag, and this is their results. Okay, for biomedical classification. Now, just this is the last topic. We have done one CNN. This is called 1D CNN. Till now, which we have we know that we have to give image to the CNN, but values, real values can also be given it. Okay. Now, this is and especially for sequential data, that is, for example, the signal, brain signal. Actually, we have done a project. It is complete, but still, as we have collected brain signals through EEG and FNIRS, we are working on it. And recently, two BTech students have worked with us, and one of scholar of my scholars in our lab, who has worked on that project on brain signal under his supervision mostly, right? They have worked on FNRS data, right? And they have used only CNN. I'm going through it. Just I am showing how the data have been, as it is my project, of course, I'm willing to show it what we have done. FNIRS data, brain signal, we have from actually, I cannot show you the subjects, the students from where we have taken. That's why I have given also here figure of other scholar. And in this case, this is a white part here. This is FNIRS device. Okay. And we are taking the signal, and it shows the activity of the brain here. Okay. And here I have tried to images of brain activation of subject while performing mental tasks or do rest. It represents so the cognitive state of the brain when it works, right? And this is the cognitive state of the brain when it is in rest. Actually, while we instruct the students that you do this task, for example, addition, right? Different tasks we have created. And we have told you solve this problem. For example, what is the time now? Only for class of class 2 or 3 students. And here you see that when they are working, this is the actually topographical image for representing the brain activity status. And if it is blue, means it is rest extreme, and if it is red, then it is highly active. So here the classification is on the two states, whether it is doing the mental work or whether it is rest. And after each work task, we have told them to take rest. Then again, we have told them to do another task. Okay. So this is just, but keep it in your mind, in 1D CNN, we have not given this image, right? Just to, in other different works, we have given the image to the CNN. But for 1D, we have not given the image. We have given the real values. Okay. And this is the proposed one. And you see Ashish Kumar, Subhashish Karmakar, Isha Agarwal, along with me, we have done this work, and the result was nice. Actually, we have compared with SVM, DNN, and proposed model. DNN is a different neural, not the same as deep learning model, right? So I am not going into the detail of it because it's more than 1 PM. So result is, you see, 93.5% classification accuracy, right? And and it is DNA is much better than this, but only to show that here we have applied the real values, okay, as the input to the CNN. And we have worked on 2 data sets. However, these are the available data set. This is not the data we have generated. There are some other works we have used our data we have collected, but this data we have collected from other papers, and they have provided the data. And in this case, you see the for data set B, that is two different data set we have used, and for data set B, HBO means actually oxygenated, right? And this deoxygenated. So this represents the active state, which we call DMT, and HBA this is the rest state we call BMT. So it gives the good result. Dataset B gives a good result, and for dataset A also the proposed model gives good result and comparable to DNN, right? So this again another slide to give the topographical
Madam, sorry to interrupt you. In the previous slide, what is HbO for oxygen and R for?
This is oxygenated. This is deoxygenated hemoglobin.
Okay, madam. This
HB
data
means hemoglobin. Oxygenated, that is when it works, it needs oxygen. Okay. And when it does not work, oxygen is less. Deoxygenated hemoglobin, and it is oxygenated hemoglobin.
okay.
This is actually the activity, level of activity it determines.
Madam, can we collect such data from any other authenticated source?
It is there, right? And we have collected this data set A and B. We have not generated it. We have not collected it. It is available in the internet, right? Website is there. We have also some data. Those we have generated. We have gone to different schools in Durgapur, and students of class 2 and 3 we have considered for the collecting these brain signals.
Okay, madam. Thank you, madam.
This is to show that 1D CNN can take real values, not the image. And this is also, you see the mental arithmetic task, what is the brain state, and this is for the rest state. However, when we instruct them, please take rest. Always, it is not really, it is very difficult to be at rest properly. So sometimes they have, maybe they have thought something else. We also, the matured people, we also cannot always take rest, okay? So these are the topographical brain images. However, again, I repeat that these brain images have not been presented to 1D CNN. We have presented the real values. So thank you very much for your patience to hear me. So if there is any questions, then of course I will be very happy. And one thing I should mention that my research scholars have worked on different domain, right? Initially I have supervised them, but after 2 or 3 years, they have become much more expert compared to me. And I am proud of them. And one of my research scholar is in NIT Rourkela, Prosenjit, and he's really expert in mathematics, machine learning. So, and if I face a problem in neural network or machine learning procedure, then I call him. And also for the project, I have a scholar now not yet submitted project, Shubhashish, for this work on 1D CNN. My name is of course there. However, the main supervisor is Shubhashish Karmakar. He has actually supervised the BTech students, Isha and Ashish, and it has been accepted in Premi in 2023 in December, very recent work. Okay. And Subhashish has also presented a work on this brain signal data, but that is hybridized with fuzzy logic. That is, fuzzy rules are also there. Thank you very much. I'm proud of my research scholars.
Madam,
Yeah.
Madam, is there any authenticated, I mean, sources to collect data about the
Yes,
waste,
yes, I can.
waste materials, madam?
No.
So that,
I should
no.
confess that I have not worked on any waste management data. Prosenjit
Okay.
has told me, I have told I know some machine learning algorithms, but I don't have, I'm not very confident in sustainability. So I was not actually, I have told, I declined it, but it's okay. You tell about the waste management. So I have, through a few papers I have gone, and just I have collected the result. Prosenjit has also helped me a lot. That's why I am here. I don't have any data, but brain signal data that I can give you, and mostly on there are some real data, however, it is available, right, in the internet for pattern recognition. And Prosenjit is there in NIT Rourkela. Prosenjit, please you respond.
Yes, madam. The thing is that, yeah, I do have some data related to waste management, and my email ID is there. So you can reach me anytime. I will provide you the data. No worry.
Yeah.
Okay. Thank you, sir. Thank you very much. Thank you, madam. Thank
And
you.
he's
Your
more
session
expert
was
than
very
me, I'm
informative,
sure
madam.
about it.
Oh, yeah. Thank you.
Yeah, and thank you,
Any other
madam, for
question?
this warm appreciation.
You are really nice. A good person, a good student, a good teacher, everything.
Thank you, madam.
So, any other question? I know you are very much hungry. I am also.
Okay, any queries from the participants end? I hope no query is there in the chat box also, nothing is there.
If
Let's go for
you
lunch,
know my
sir.
email ID, and also in the website you will get everything, so you can communicate with me, and also Prosenjit will give better answer, right? And you can discuss directly with Prosenjit.
Okay. Thank you,
Okay.
madam. Thank you.
Thank you.
Hello.
Thank you, ma'am.
Yeah.
Hello.
Thank you, madam.
Yeah.
Hello.
Yes.
Madam, am I audible?
Yes.
Yes, you are audible.
Yes. But I have a small doubt actually. Thank you
Yeah.
for your informative session.
Yes.
But you told that regarding the brain signals, your team approached to the different schools in Durgapur to collect the data. So I
Yes.
have a small doubt that whether any sort of ethical permissions are required to
Yeah.
collect the brain signals.
Sure. We have done
Okay.
every steps of it.
Okay, so could you please just
Parent
enlighten us or little bit guide
yeah.
us actually to form that ethical committee, how to take the data and all these things? I mean, how to.
Okay. You just give me a mail. I will share with you everything.
Okay, I mean, what
We
is the
have a
process?
ethical committee also here, institution, as per the guidance law of government, right? And experts from different hospitals are also here. We have done it, and also the parent consent form, we have collected it from the parent. We have talked to the teachers have talked to the parent. Many steps are there.
Okay. So, madam, could I get your email ID, please, so that
You
I
will
can.
get it in our website of NIT Durgapur.
Okay, thank you.
tpal.csc, very easy to remember.
Okay.
tpal.csc@nitdgp.ac.in.
Okay, ma'am. Okay, so I will
Or
set
Tandra.
okay, I will send a mail to you actually regarding the
Okay.
guidance
Okay.
of
I'll be
formation of
happy
ethical committee.
if it can help you.
Okay, thank you so much.
So can I leave?
Yes, ma'am. Thank you, ma'am, for your very beautiful and informative presentations.
Very
Okay.
much happy.
Yes. So thank you giving your valuable time. So thank you, ma'am.
Okay. Bye. Goodbye.
Bye.
Okay, thank you, madam.
Thank you.